Hello and thanks for watching. In this video I'm going to talk about time as a dynamical variable. This is a brief introduction to the ideas presented in this article, an accumulative model for quantum theories, which was published in the Electronic Journal of Theoretical Physics. So let me give a brief outline. First I'm going to talk about some so-called obvious facts, which may not actually be facts at all. I'm going to provide some mathematical suggestions for a different way of looking at things. I'm going to look also at path integrals, which are very foundational in quantum field theory, and look at those also in a different way. I'm going to draw an analogy between physics and communications. My own background was in communications engineering, so that was in some way the inspiration for this analogy. I'm going to describe some experimental predictions of this new model of physical reality. I'm going to present some consequences and then draw some conclusions. So first, let's talk about some obvious facts. First of all, I am a stationary observer. That's obvious. I'm standing still, I'm not moving. Now, however obvious it is, it's not true. Another obvious fact is that time is absolute. All observers' time measurements agree. Both of these obvious facts are not actually true. Now, why are they so obvious? Because they follow from our everyday experience that we have every day. And the problem is this is our experience. As observers, we're biased. We base our presuppositions on what we observe on a daily basis. So when we break out of our usual observational mode, we find out that our biases are not well founded. So the upshot is be wary of obvious facts. For thousands of years, people thought that this was absolutely true, philosophical truth. Now we know that if we look at the universe in such a way that we see we are not stationary, but we are moving, and that all motion is relative, and that time itself is not absolute, but time is relative, then we get a much clearer picture of the way the universe works. So be wary of obvious facts. Now, here's another obvious fact that we take for granted, and physicists still take for granted. The universe evolves dynamically as a function of time. All the important physical equations, from Newton's equations, Maxwell's equations, the equations of quantum mechanics, all evolve as functions of time, where time is the independent variable and the coordinates and fields are dynamical functions of time. Now, could this obvious conclusion also be the result of observational bias? Is it possible that this picture of the universe as a dynamically evolving structure is not the whole story? Well, let me give some mathematical suggestions that indicate that perhaps this is the case, that this evolutionary picture is not really the whole story. Right now, throughout the history of physics, mathematical formulations have suggested physical mechanisms. For instance, Planck's law. Planck's law started out as an empirical law for the radiation from a black body, and from that, Planck inferred that radiation was emitted in discrete chunks or quanta. And there are many other examples of how the mathematics has suggested physics in statistical mechanics and even in quantum mechanics. So mathematics drives analogy, which drives physics. All right, so let me put forward some analogies that suggest an alternative picture of the universe, not as an evolving process, but as something more static. Now, the principle of least action is a fundamental principle in classical mechanics, and what it says is that if you fix 2 points in space-time, then the path that a particle travels from one point in space-time to the other point in space-time minimizes a certain quantity called the action. Now, if you compare this to a hanging cable, if you fix one end and you fix the other end, then and you hang a cable between the two ends, the cable will take the shape that minimizes the energy. Now, how does the cable attain that shape? Well, there's a process. The cable, when you first hang the cable, it's not in minimum energy, and it arranges itself to minimize the energy. So there's a process of minimization. So you might think that in least action, in order to minimize the action, there should be a process of minimization. The problem is, in least action, the endpoints are space-time and not space. When you have a hanging cable, the endpoints are spatial points, and you have a process in time that minimizes the energy. Now, if you're having the endpoints be space-time points, then you can't use time as the independent variable in which the process proceeds. Well, so this suggests that there's a process in some other dimension that's producing this minimum configuration. So it just suggests. It doesn't say, it just suggests. Now, another suggestion is the idea that space-time is a manifold. It's a connected whole. Space and time rotate into each other. There's really no special distinction between space and time. Well, there's kind of a distinction between time-like and space-like directions, but it still seems to be a continuous fabric, kind of like a bubble or something. So it's a space-time manifold picture suggests that space-time is a fully formed surface and not a process, which is a function of an independent variable. So it suggests space-time is not something that's unfolding, but something that is fully formed because of the integral relationship between space and time. Another suggestion are two theories called Feynman-Wheeler electrodynamics and transactional quantum mechanics, which I'm not going to go into in that much detail. But in these theories, it shows that what we think of as causation in physics, Feynman-Wheeler in electrodynamics and transactional quantum mechanics, who put forward by Kramer, these both imply that what we call causation may actually be due to correlation. There's a long-standing philosophical debate about how to distinguish correlation from causation, and in this case, the physics, you cannot clearly identify electrodynamics and quantum mechanics as causal, and what appears to be causal may just be something to do with correlation. This last one, the many worlds interpretation, is an interpretation of quantum mechanics, and I'm going to pass by this. It's a little bit technical. I may talk about that in another video. All right, so these are all suggestions that the picture of the universe as an evolving process may not be the most insightful picture of the universe. Now, here is a path integral. Now, path integrals are fundamental to quantum field theory, which is considered to be the deepest theory that we have of physical reality. It explains quantum phenomena. It also explains the creation and annihilation of particles, which regular quantum mechanics cannot. Now, the basis of quantum mechanics is path integrals. Here's a path integral. And what this is saying is that the probability of a particular state U is proportional to the absolute value squared of the integral. Now, this says integral, but when I see integral, I think sum. An integral is always a summation. So you're summing over what are called paths in a certain path space, and you're summing this quantity, the exponential of the action. I'm using units where h bar equals 1. So here we have a sum of quantities over paths, and each term in the sum is e to some quantity. All right, now, when a physicist looks at this and sees a sum of terms that are proportional to e to an exponential, some physicists might think, well, it looks like a partition function in statistical mechanics. The only difference is that instead of a negative quantity here, you have an I. Well, this was a very fruitful insight, and it led to Euclidean quantum field theory. Now, a communications engineer looks at this and sees something completely different. When you see I e to the I s gamma, that looks like a wave. Looks like a radiated wave. And when you're summing those, this looks like multipath, which is something that communications engineers deal with all the time. In wireless transmission, when you're transmitting from a source to a receiver, the signals bounce off various directions and they add together either constructively or destructively. And the total signal becomes a summation of exponential terms that look just like this. So this suggests an analogy. which I'm going to delineate in the next slide. So here's my first, here's an analogy. Consider a radio receiver which is tuned to a certain frequency, and this receiver wanders randomly around in a static environment where signals of the same frequency are present. So this environment is full of signals with the frequency that the radio receiver is tuned to. Okay, the receiver accumulates its received signal and logs a detection when the amplitude of the accumulated signal reaches a threshold. So it keeps on detecting, and it accumulates this signal. There are accumulator circuits in electric circuits, and once it reaches a threshold, then it logs a detection. Now this is actually somewhat similar to how cellular phones detect base station signals. So it is through a process of accumulation. Now what's very interesting about this process is that if we consider a case where the receiver is wandering around for quite a bit of time and even can be wandering all over the space, the allowable space, then the probability density for the receiver's location at the time of detection may be shown to be proportional to the mean squared complex amplitude of the signal at each location. So if I'm at a location, what's the probability that that's the location that the receiver is going to log its detection? Well, that's proportional to the mean squared complex amplitude of the signal at that location. Now, if you're familiar with quantum mechanics, this should ring a bell. You have complex amplitudes. The wave function is a complex amplitude, and the probability is proportional to the absolute square of that complex amplitude. So there's some surface similarity here. And here we do have a process of accumulation, which is the kind of process that's suggested by path integrals, that you have some kind of sum of terms, and then you take the mean squared amplitude. So this does contain certain elements that are promising to show us that we have something that's analogous to quantum mechanics. So let me make that analogy more explicit. In the communication scenario, I had a radio receiver that moved randomly in space as a function of time. Now, in my space-time scenario, where I'm trying to explain the formation, existence of space-time, instead of a radio receiver, I postulate that there's what I would call a pre-space-time. And what's a pre-space-time? It's kind of like the space-time we see now, a complete space and time, but it's not what we see realized. It's a possible space-time, and this pre-space-time is evolving as a function of another parameter that is not evident in the physical world. It's extra-physical. I call this parameter alpha. So you think of the universe as a bubble that's evolving, and it turns out that the actual universe that we see can be compared to one snapshot of that evolving bubble. And that's not just the universe at this current time, but all of space-time is a snapshot of this evolving bubble, which is evolving in a non-space-time dimension. Okay, so we have this evolution in a non-space-time parameter, which is analogous to this radio receiver moving randomly in space as a function of time. Now, the radio receiver is moving in a static, space-dependent radiation field. In the space-time scenario, we have a driving oscillation. Now, this static space-dependent radiation field produces an oscillation on the radio receiver, and it changes the amplitude of the radio receiver's oscillation. So in lieu of that, in the space-time scenario, I have a driving oscillation as a function of alpha, whose complex amplitude is given by this psi, which is analogous to the wave function. So this wave function is a property of the configuration of this pre-space-time. Now, this oscillation is not oscillating in time, it's oscillating as a function of alpha. Okay. Now, in the communication scenario, we had a process of singular accumulation in time. In the space-time scenario, we have a driven harmonic oscillator whose complex amplitude varies with alpha. So the harmonic oscillator is associated with the evolution of the universe in this non-space-time parameter, and it varies as alpha varies. In fact, it grows because as the pre-space-time configuration changes, it causes random changes in this harmonic oscillator, which tends to make it grow. Now, the receiver, in our communication scenario, the receiver has a particular location when the signal amplitude reaches a set threshold. Now, in my space-time picture, space-time is actualized when the oscillator's amplitude reaches a threshold. So once the threshold is obtained. We get our snapshot, and space-time is what we obtain. And again, I say it's all of space-time, not just a snapshot in a particular time, but all of space-time is actualized as a single snapshot. By the way, this has to do with the collapse of the wave packet. This shows that there is no collapse of the wave packet in time. The collapse actually occurs, all of space-time collapses at a single time, because you're taking this one snapshot, this one threshold, and that's when the space-time is actualized. No, the probability distribution of the detection location in our communication scenario is proportional to the squared complex signal amplitude, and in the space-time scenario, the probability of configuration U is proportional to the wave function squared. So we have a very clear analogy between communications and space-time. If you want the rigorous details of this analogy, I refer you to the paper. I just want to give you the ideas in this talk. Okay, now, this would just be in the realm of theory if it did not predict anything experimental, but in fact we can derive an experimental prediction from this picture. Since the process of accumulation is random, then we have jitter. If we have jitter, then you don't simply have the probability proportional to this path integral squared, but there's another term that's due to jitter. Now, what about, does this small term make any difference? Yes, because when this quantity is relatively small, this is relatively larger. When this quantity is relatively large, this quantity is relatively insignificant. So what happens is that this effect of jitter will tend to slightly amplify small probabilities at the expense of larger ones. So if this picture is correct, then this should be an observable effect when you look at probability distributions predicted by quantum mechanics. Unfortunately, I can't predict the size of this effect because we don't know the size of the jitter. All right. So what are the consequences? Consequence is there are very great conceptual differences in how we view the universe. First of all, temporal causation is an illusion. It's really correlation and not causation. What seems to be causation is the fact that there's an evolution that takes place outside of space and time that we don't see, and that evolution produces both the past and the future occurrence, and they're linked because they both have a common source. Now, a local causal theory is possible if space-time itself is caused by a process in another parameter. Now, it's quite well known that a local causal quantum theory is impossible if you restrict yourself to space-time. Now, you can solve that problem by seeing that space-time is not complete in itself, but it's the outcome of a process. In that case, the process is local and causal. Now, all quantum paradoxes can be eliminated by viewing space-time as the outcome of a threshold accumulation process. And I can justify that briefly by saying that this picture justifies the path integral picture, and the path integral picture is the mathematical foundation for quantum mechanics. So all paradoxes follow from the path integral picture. So if I've explained the path integral picture, I've explained the paradoxes. The wave function is actually a physical field which affects the dynamics of the evolution. It's not just an expression of partial knowledge, but it's an actual physical field. This viewpoint predicts elevated probabilities of rare events without affecting eigenvalues. So I want to emphasize that the eigenvalues, it's only the probabilities that are affected because of the interpretation of this accumulation interpretation. The eigenvalues are not affected because the wave function is not changed. The wave function is fixed. It's only the way that the wave function produces the probabilities that creates the change in probabilities. Okay, so my conclusions are two that you can read. I especially like the second one. I seem to have been only like a boy playing on the seashore while the great ocean of truth lay all undiscovered before me. This is a quote from Newton. What this picture would say is that in fact all of space-time is like a seashore, and we only see what washes up on the shore, and we don't even have access to the great ocean of truth. Thank you very much for listening.